Okay, and this video starts the long exploration into a series, infinite series that converge. So basically, I just want to get over some vocabulary first because there's a lot of different words that get floated around, and it's important that we understand what's what. So we start off with, remember the definition of a sequence. A sequence is simply a list of numbers. So this sequence I've defined here as 2n plus 1. We know this is an arithmetic sequence with common difference of 2. In this sequence, we can just list the numbers as shown, or we can express the sequence as a series. The difference between a series and a sequence is the series takes the sequence and adds all the terms together. So what we're going to be exploring is this fact. Some series converge and some series diverge. How can we tell from looking at a series and understanding its nature whether or not we will get a sum? So what that sum is, that's another issue, but for right now it's simply a matter of yes, there is a sum, or no, there isn't. So in order to do that, we need to be able to understand what a sequence of partial sums is. So basically we start with a sequence which becomes a series, and we're going to turn that series into another sequence in and of itself. We call that a sequence of partial sums. The first number in the sequence is s sub 1, which is the first number in the original given sequence, but the second number in the sequence of partial sums is the first term of the sequence plus the second term of the sequence, and so that gives us 8. S sub 3 is the first 3 terms added together, and so on. So S sub n will be the first n terms added together, 3 plus 5 plus 7, and so on. This again is another arithmetic series, therefore we can sum the arithmetic series using our summation formula for arithmetic series, and that means that the nth partial sum, that is the total of all of the different numbers added up in the sequence up to n equals n, okay, equals n I guess, would be this number, 2n times, or plus n squared. Since, well, here's the big idea here, if the sequence of partial sums of this series converges, then the series itself converges. So, in other words, if we take the limit of s sub n, and it actually has a limit, then we can say that the series converges, this series up here, which is the sum of all numbers in the sequence. So, in this case, the limit as n approaches infinity of this quadratic expression here is going to be infinity, and therefore we assume divergence. So here again, as an example, we have the sequence, u sub n, and we have the series where we add up to infinity all the terms. So in other words, the series we're going to be exploring is 1 over 3 to the 0, plus 1 over 3, plus 1 over 3 squared, and so on. The sequence of partial sums now is going to be 1, 1 plus a third, 1 plus a third plus a ninth, and so on. And this, again, turns out to be a geometric series. Not again, this is the first one we've looked at in this video, but here we see a geometric series because the common ratio between each of the terms is going to be 1/3. So that's the r value. The first term is 1, therefore we can actually find the sum s sub n by taking the limit as n goes to infinity. We get 3/2. So since the limit of the partial sums exists, the series converges. So there again, what I did was, I was a little bit skimpy with my language here, but basically I recognized this as a geometric series in and of itself, and geometric series can be summed to infinity using this formula, so I skipped ahead. Rather than taking the limit, I just evaluated using our summation formula. Anyway, since we learned how to determine convergence on sequences, and now we can express a series as a sequence of partial sums, then we can apply what we learned about sequence convergence to series convergence. But it's important, again, that we understand the 3 different things we're starting with. We're starting with a sequence which is converted into a series, and that series is converted into a sequence of partial sums of said series. So make sure you keep those straight. So, if a series is convergent, then the limit as n approaches infinity of the sequence that created that series will be 0. So this is a fact that kind of emerges out of what we just explored with convergence of partial sums. However, we need to be careful with this because just because the limit of u sub n approaches 0, that doesn't mean that the series converges. The series may converge or diverge. We're going to explore this later, but just to make sure you understand, this particular series, k goes from 1 to infinity of 1 over k squared, this converges, and you will observe that as I let k approach 0 is 0. Well, that might make us think then that if we start with this condition about the limit, then we can assume convergence of the series. However, it's not true, because when we explore 1 over k and let k approach 1 to infinity, this in fact diverges as a series. However, the limit as k approaches infinity of 1 over k is infinity. Remember, that turns out to be a natural log kind of a situation when we use the integral test. So the point of this is just because the the expression or the sequence that's given, just because the expression itself has a limit that approaches 0, doesn't mean that the series of that sequence will converge. But we can go the other way around and say if we do know convergence, then we will also know that the limit has to approach 0. So we'll see how useful that is, but it's just a little bit of a lesson in logic and reasoning and so forth. All right, so here's some, actually I'm going to stop, and this is part 1 of this particular video series, and I'll look at some examples of what the Cambridge text wants you to do to understand the difference between partial sums and so forth. So, thank you for watching.